Hi there, folks. Today we're looking at perimeters and areas of similar figures. And if you recall, similar figures are figures that are the same shape but different sizes. And the criteria for things being similar figures is that all the sides had to be proportional, so the corresponding sides had to be proportional, and the angles all had to be congruent. All right. And so here it says find the area and perimeter of the regular polygons. The thing that you need to understand is if these are regular polygons, then all the angles are going to be congruent within each polygon, which means they're automatically congruent to the corresponding angles of the other polygon. All right. And likewise, if it's a regular polygon, then all the sides of one polygon are congruent. So that means they're automatically proportional to the sides of the other polygon because those are also congruent. So the ratios will automatically be the same. So anytime we have regular polygons, they're automatically similar polygons. And so if I look at this first one, right away, regular polygons, all the sides are the same. So that means this one is an equilateral triangle, so all of the sides are 8 inches. Likewise, all the sides here are 4 inches. And so if I kind of look at the larger triangle and the smaller triangle separately, the perimeter of the larger triangle is 24 inches. It's just all the sides added together. The perimeter of the smaller triangle is just all the sides added together. That's going to be at 12 inches. Okay? And so then we want to find the area of this thing. To find the area, I need the height. So here for the height, I'm just going to drop an altitude down through this thing. Same thing with this guy. And keep in mind, because these are regular polygons, maybe before I drop that height, let's talk about this as regular polygons. That means that all of these angles have to be the same, so they're all 60 degrees. And likewise, in the second triangle, they're all 60 degrees. So now, as I drop this perpendicular, it gives me two right triangles, and each of these is a 30, 60, 90 triangle. Okay? And because it's a 30, 60, 90 triangle and I have the hypotenuse, I can easily find the missing sides. This side down here is going to be 4 inches, and this side over here is going to be 4√3 inches. And again, that's just using my special triangle. Remember, the hypotenuse to the short side, I divide by 2. To get from the short side to the long leg, I multiply by √3. I could do the same thing in the other polygon here, in the other triangle, because I know that this is 60 degrees and this is 30 degrees. So I have that special right triangle of a 30, 60, 90. Again, I divide the hypotenuse by 2 to get this side down here, the smaller side. And then to get the longer leg of this thing, I multiply by √3. Okay, so now I can use this to find the area. All right, area of a triangle is 1/2 the base times the height. So for the larger triangle, 1/2 the base times the height, that's 1/2 times 8 times 4√3 is going to give me a 16√3. And that's square inches. The area of the smaller triangle, once again, 1/2 the base times the height. So 1/2 the 4 times the 2√3 is going to give me a 4√3. And that's, again, square inches. All right, so I've found the perimeter and area of each of these. In a little while, we'll actually compare these things in terms of the ratios that they give us. And so just a reminder of the ratios for this particular triangle. When you look at the overall triangle, you compare the proportionality of the sides, it goes from 8 to 4. The scale factor here, we would say going from the big triangle to the small triangle is 1/2. In other words, to get from the big one to the small one, I multiply by 1/2. And so if you compare that in terms of the perimeter, check out the scale factor right here for the perimeter is also 1/2. Okay? But the scale factor for the area is not. The scale factor for the area to get from the larger to the smaller is actually 1/4 for this one. Okay? So just something to think about and keep in the back of your mind. If I look at this one, once again, if these are regular polygons, they're automatically similar, because if they're regular polygons, then all of these have to be right angles. See, if they're regular polygons, a quadrilateral, these are each squares. Okay? And when we look at this, all of these sides are the same. Over here, all the sides are the same. And so as we look at this thing, if I want to find the area and the perimeter here, again, I'll do the smaller one first this time since it's listed first, and then the larger one. So the smaller one has a perimeter of 12 inches, and the larger one has a perimeter of 36 inches. So now moving on to the area for this one, I can go right to the area. I don't need to find anything. It's just base times the height, like a parallelogram. And so the area of this first one is 9 square inches. The area of the larger one, once again, base times height, is 81 square inches. And once again, if I start to think about this in terms of the proportionality of the sides, going from something like a 3 to a 9, well, the scale factor here is a 3. It's 3 to 1. Okay? And so if I multiply by 3, it gets me to the larger of the two squares. But now compare that over here. To get from the small one to the big one, well, yeah, that's also times 3 when we look at the perimeter. But for the area, it's times 9. Okay? And so this is the kind of thing we want to investigate. We want to look at this and say, okay, how does the proportionality change as I go from the side length to the perimeter to the area? Okay? And so we want to think about this. How did the perimeter and area compare to the scale factor? Well, in the first one, the scale factor was 1/2 for the sides. Okay, so that was the actual scale factor. But then the ratio for the perimeter was also 1/2, but the ratio for the area was 1/4. In the next example, the scale factor, in other words, the ratio for the sides was 3/1. For the perimeter, it was the same thing, 3/1, but for the area, it was 9/1. And hopefully you can kind of understand and pick out the relationship here that the perimeter has the same value as the scale factor. That's the obvious one. But the area has the same scale factor, but it's squared. And so when you look at this guy is the same. It's like the scale factor to the first power. But this guy is like the scale factor to the second power. That's how we get a 1/4. Likewise here, this one is like the scale factor to the first power, so it's the same. But the area is like the scale factor to the second power. And so that's the relationship that exists here. And when you think about it in terms of the units. When you compare the corresponding sides, you're comparing units to the first power, inches to inches, or feet to feet, or meters to meters. Okay? They're inches to the first power, so they have the same relationship, the same scale factor. When we talk about area, think about the units now. Instead of inches, it's inches squared. Instead of meters, it's meters squared. Instead of feet, it's feet squared. And so what happens, instead of the same scale factor, it's that scale factor squared. And so the area has a squared relationship as opposed to the perimeter, which has the same type of relationship, that linear relationship. Okay? So perimeter and area of similar figures. If I have similar figures, the perimeter, the ratio of the perimeters are equal to the scale factor. So basically, the ratio of the sides and the ratio of the perimeter are the same thing. And again, think of it in terms of measurements. Because it's still linear measurements, the scale factor doesn't change. The scale factor is the same for the perimeter as it was for the sides. And so the ratio for the perimeter is the same as the scale factor. But the area, because now we're squaring this thing, it's squared units, the ratio of the areas is equal to the scale factor squared. Okay? So it's the same relationship, but squared. All right? And so when we talk about the proportionality of similar figures, we've been talking about the scale factor. It's just the ratio between the sides of the similar figures. The perimeter has the same ratio, and the area has that ratio squared. Okay? For example, if I look at this guy, it says find the ratio for the perimeter and the area. And so once again, if you kind of think about this as a ratio between sides, so let's compare the corresponding sides. The ratio between corresponding sides is 6 to 9. Or, if we reduce that, 2 to 3. Or write it as a fraction, it's 2/3. Okay? And so that becomes like the scale factor to go from the big one down to the small one, right? Watch this. 9 times 2/3 gives me the 6. Okay? And if I wanted to go the other way, I would use a scale factor of 3/2. Okay? And so it's just a matter of which way I'm comparing this thing. If I compare to the small one to the big one versus the big one to the small one, of course my ratio will be reversed. Okay? And so let's think about that relationship. And so if we think about it, using either one of these scale factors, let's say I used the second version and said, hey, the scale factor is 3/2 to get from the small one to the big one. So that means the ratio for the perimeter, when I kind of think about this, let me start with this ratio right here. The ratio of the sides was 2:3, so the ratio for the perimeter is also 2:3, which means the scale factor is also 2/3, or going the other way, 3/2. It'll be the same relationship. But then I could do the same thing with the area and say, hey, you know what? The relationship for the area is not the same as the ratio for the sides. It's that ratio squared. And so if you square each of these, the new ratio is 4:9. That's the ratio when we compare the areas of these two things. Okay? And we could also think of it this way as 4/9. Or if I want to think of it as a scale factor going the other way, it would be 9/4. And the reason I'm writing the scale factor both ways is because it depends, which one of these we use depends on which thing we're trying to get to and which thing we have. If I want to go from the small shape to the larger shape, then I need the larger scale factor. I need to multiply by the 9/4 for area, or the 3/2 for perimeter. But if I want to go from the bigger trapezoid back to the smaller trapezoid, then I need the other ratio. I need the 2/3, or the 4/9 if we're talking about area. That's why we have to understand how to write this both ways, okay? So when we think about the ratio, it's 2:3 for the perimeter, same as it was for the sides. It's 4:9 for the area. It's the squared version from the sides, okay? And then depending on which figure you're starting with, we would use a scale factor of 4/9 or a scale factor of 9/4. It's just a matter of which way we're comparing and which way we're writing the ratio, okay? And then continuing the same example, it says if the perimeter and area of the smaller trapezoid, so we're talking about the same trapezoid, so let's say this smaller trapezoid has a perimeter of 28 meters and an area of 36 meters squared. Okay, so 36 square meters. I want to find the perimeter and area of the larger trapezoid. And so here's the thing. If I were given one of the sides of the smaller trapezoid, let's say the 6 meters, I could use this scale factor to find the side of the larger trapezoid by just multiplying by 3/2, multiplying by the scale factor. And when you do that, you get the side length of the larger trapezoid. And so if the perimeter has the same relationship, I can come up with the perimeter of the larger triangle by multiplying by the same scale factor, by 3/2. And so when I do that, it gives me the area of the larger one. Let's see, 3 times the 28, and then divided by the 2 gives me a 42. All right, switching colors. So 42 meters. And so without even knowing the rest of the dimensions of the larger trapezoid, I can find its perimeter based on its relationship to the smaller trapezoid. Likewise, when I look at the relationship between area, instead of using a scale factor of 3/2, I'm now going to use a scale factor of 9/4. It's the squared version of that same scale factor. And so once again, I do 36 essentially times the 9 divided by 4, or divided by 4 times 9, and it gives me the area of the larger trapezoid as 81 meters squared, 81 square meters. And so without actually finding the values I need in that larger trapezoid and finding the area of that individually, I can simply multiply the area and perimeter of the original trapezoid, of the smaller trapezoid, to get the larger one, okay? The other option here is you could think of this in terms of proportions. You could look at it this way and say, hey, the proportion for the perimeter is the same as the scale factor, it's 2/3. The proportion for the, or the ratio for the areas is then going to be 9/4. And then you could solve this like a proportion. You could say, hey, the perimeter is 2/3 equals, well, that's small to big, so here, small over big. You can cross multiply and solve, and you'll get the 42 that we ended up with, okay? Likewise, using the same ratio, the same type of scenario, the ratio for the areas is 4/9. That was big to small. So over here, the ratio for the areas is big to small. And if you cross multiply and solve, you'll get x equals the 81. Okay, so there's two ways to do this. You can either think of it as a scale factor and multiply. You just have to make sure you use the right scale factor, or set it up as a proportion. You know the ratio for perimeter, you know the ratio for area, and just like any other proportion, you just have to be consistent. If the first ratio is small over big, the second one has to be small value over big value. If the next one is small over big, the other, or big over small, then the next one has to be big over small. Okay? If we look at something like this guy, it says find the perimeter and area of each regular pentagon. And so once again, we think about the relationship here. Look at what you have to do to get from side to side. So here, you would multiply by 2. And so if that's the relationship between the sides, the relationship for the perimeter is literally the same thing. So it's times 2. And if you multiply by 2, that gives me a 40 centimeters. Okay? But now the relationship for the area, instead of times 2, is actually going to be times 4. It's going to be that same relationship, but squared. So here was times 2, here was times 2, but here it's times, well, whatever 2 squared is. Okay? So for that one, we're actually going to multiply by 4. And so that's the relationship when we look at this thing. Likewise, if we kind of skip over this one, let's kind of start over here. Say, all right, to get from here to this one, it's times 3. So the relationship for the perimeter should be the same thing. It's times 3. So the perimeter of this one is going to be 60 centimeters. But now when we look at the area, and this is the one that's a little bit tricky, instead of the same relationship, instead of times 3, it's that same relationship but squared. So it's actually going to be times 9 for this one. So that gives me a 247.5 squared. Almost forgot my little squareds on those, okay? If I look at the next one, same kind of thing. Let's look at the relationship between the small one and the big one. From here to here, the relationship is times 4. So for the perimeter, it's going to be that exact same relationship, just times 4, and that gives me an 80 centimeters. But the relationship for area, well, it's kind of like that relationship, but instead of times 4, it's that same relationship but squared, so it's actually going to be times 16 this time. And so that gives me a 440 square centimeters, okay? That's the relationship, okay? And that's the thing we need to understand is, okay, how do I adjust the ratio to use it for perimeter? How do I adjust the ratio to use it for area? We don't need to adjust the ratio, and the answer is we don't need to adjust the ratio for perimeter. It's the same as the ratio for the sides. For area, we square the ratio we had for the sides, and that can give us the area of the new figure, okay? And see, that's important because that means once I've found the area of one of these regular pentagons, I could use that to find the area of any regular pentagon, okay? For example, it says the area of two similar figures are 875 square feet and 135 square feet. Find the ratio of the perimeters. And so once again, if I look at this as a ratio, if I said, hey, what's the ratio of the areas? If I were to take this and just kind of simplify this ratio, and you can use a calculator, they're obviously each divisible by 5, but probably a little bit more than that. So if I simplify this thing, let's see, I think I can simplify it all the way down to 9 over 125, okay? And so once this thing is simplified, that's the relationship. That's for the area of this thing, which means that's a squared relationship. Which means if I want the ratio of the original of the perimeter or of the sides, I have to take the square root of that to get the ratio of the sides. Okay? And so I want to leave this in exact terms. That's going to be a 3 over. Well, this one, that's going to be the 5 root 5 when it's completely simplified, which means this is my ratio between the small and the large. And I'm not going to rationalize this denominator only because I could have written this the other way. Okay, so understand that we can go back and forth with this thing. If I have the ratio for the perimeters, I square it to get the ratio for the areas. But if I have the ratio for the areas, working backwards, I could take the square root to get the ratio for the perimeters. And likewise, that would then be the ratio for the sides of this polygon. Okay?